much. So it's a pleasure to be here. Unfortunately, we couldn't be in Israel to see everyone in person, but hopefully next FPSAC. So there are some complicated words in my title, so let me unpack some of them. So I will start from Hurwitz numbers. And the Hurwitz numbers are some numbers that were considered by Hurwitz in the second part of 20th centuries. So Hurwitz was interested in the following problem. He wanted to understand branched coverings of the sphere, and he wanted to classify or let's say count them. So if you don't know what are branched coverings of the sphere, I have this little picture that should help you to understand. It's a fairly simple object. So you should think that this is basically the same as covering of the sphere, which means that in a generic point, there is a small neighborhood that the preimage of this neighborhood looks just like several copies, disjoint copies of this neighborhood. But there are these points. So there is a finite number of points on the sphere, such that your coverings around these points look a bit differently. And if you look at the very small neighborhood around these points, basically your covering, your function looks like z to power n. So this is a function which maps in local coordinate. It maps a unit open disk onto a unit open disk. So this problem seems to have nothing to do with combinatorics. It's a geometric problem, but the brilliant observation of Hurwitz was that in fact it has a lot to do with combinatorics, because counting these branched coverings is equivalent to counting factorizations of an identity in the permutation group. So this is what he did, and if we want to count things like that, because we're combinatorialists, we are immediately thinking that perhaps a good idea is to look at the generating functions of these objects. So I have this quite complicated generating function because I would like to keep as much information as possible. So I have infinitely many parameters here. There are these variables p's, and in fact, this is a finite number of infinite families of variables, such that every family pi is telling me what is the cycle structure of the ith permutation. So this tau k, this is a exponential generating function of factorization of an identity, and my pi's are telling me what are the cycle types. So here is an example. For instance, if I have this factorization of identity into 3 permutations, the associated variables will be P1 and P4 for the first permutation, because I have one cycle of length 4 and one cycle of length 1. It will be P1 to power 3 times P2 for the second permutation, because I have 3 fixed points and 1 transposition. And for the third permutation, it will be P5. Okay, so this is also a standard combinatorial trick to start from labeled objects and consider an exponential generating function, and then to notice that if you look at the logarithm of this generating function, and if you take the derivative with respect to t, where t is a variable which is telling you what is the size of your symmetric group, then what you've got is actually generating of non-labeled but rooted objects which are also connected. So these two things, rooted and connected, I will go back to these two notions later so that it will be more clear what I mean. An important thing is that this function tddt logarithm of tau k, this is basically a generating function of branched coverings. Okay, so we formulated this geometric problem into a combinatorial problem. And these Hurwitz problems was forgotten for a while, and in the second half of the 20th century, people started to be interested again in this problem because they found out that there are many, many different connections with other areas of mathematics. So the first connection I would like to tell you about is a connection of symmetric functions. I will recall that Pi is a power sum symmetric function. So this is just a sum of x's to a power I. And then a sure symmetric function, it can be defined by telling you that the transition matrix between sure symmetric functions and power sums is given by characters of the irreducible representations of the symmetric group. So if you know what are sure symmetric functions, you might be unhappy with this definition because there are many different definitions equivalent, and this is probably definitely not the standard one. But for our purposes, this is the most convenient definition, and here is why. It is because there is this very nice formula of Frobenius, which is telling you that if you want to understand what is the multiplication of central elements in a group algebra, you can use representation theory to do this. So basically, we are interested in factorizations of identity. So what we are interested in terms of group algebra, we would like to see what is the multiplication of conjugacy classes in the group algebra of the symmetric group. And then Frobenius tells you that, well, you can count these coefficients using representation theory. So, okay, how this is related to our tau function that I showed you on the first slide? Well, it's a direct and a very quick corollary from this Frobenius formula that our tau function is in fact the partition function of sure symmetric functions. What you need to do, you just look at the definition that I showed you of sure symmetric function, and you remember that your tau function is a generating function of factorizations of an identity, and then you apply Frobenius character formula. So this was a discovery. It was not a discovery of Hurwitz. It was discovered much later. And this is the first connection between these branched coverings and the symmetric functions. But there are more interesting connections. And before I will get there, let me just mention that this tau function that I defined, it's a very, it's tracking a lot of information about your factorizations because I have this infinitely many variables. I have a finite collection of infinitely many variables. So I know pretty much everything about my factorizations. But in most cases, I don't need that much information. And especially people who are interested in Hurwitz numbers, they're typically interested in a case where except two permutations in your factorizations, all the other permutations are transpositions. So one special case of my tau function is when I substitute for all the other variables except the first two, just variable u. So I keep the first two infinite families of variables, but for the rest infinite families, I forgot what is P1, what is P2, what is P3. I just set them all to the same variable. And if you look at this generating function, it turned out that this is a fundamental object in this field. This function has many beautiful properties, and a very important property that was discovered by Okunkov, Orlov, and Pandaripande at the beginning of 2000 is that this function is a tau function of certain integrable hierarchies. And since then, this function became really, really important in the field, and it got a lot of attention. There is also a second important case for us, and this second important case is slightly different, namely, I don't want to kill these infinite families of variables, but I don't want to have too many of them. So I will keep only 3 infinite families of variables. And again, from geometric point of view, this model is very important because this is something which is called Grothendieck descent d'enfant. So again, in terms of branched coverings, this is a branch covering which has precisely 3 branch points. And this is a particularly important model, but in terms of combinatorics, this is also a very nice model because you will see now that it is related with counting certain nice combinatorial objects, which are called bipartite maps. So I will explain what are bipartite maps by showing you an example how to create a bipartite map from my triple of permutations, whose product is equal to identity, and this procedure is in fact a bijection between labeled bipartite maps and this factorization of identity into 3 permutations. So I have these 3 permutations, and I put these little indices: a black dot, a white dot, and a little square. So this is because they will play the particular role. So you might think that the first permutation with a black dot is telling you something about black vertices in your bipartite map. A white dot is telling you something about white vertices in your bipartite map. And this last permutation with this little square is telling you something about faces of your map. Okay, so what are these maps and how this procedure looks like? What I do, per each cycle of the first 2 permutations, I draw vertices, and I also draw half edges going out from them. And then I labeled these half edges clockwise in the same way as my cycles. So for instance, here I have a cycle 1, 2, 4, 5, and this means that if I walk clockwise around this vertex, I see 1, 2, 4, 5. So this is a procedure, and now an obvious thing to do is to connect half edges with the same label. So if I do that, I obtain a bipartite graph, but notice that this bipartite graph is also embedded into a surface, because when I was drawing it, I had this convention that I have this clockwise orientation around all the vertices. So in fact, I connected these vertices in a very particular way. So this means that my drawing is in fact an embedding. So we can think that this is a ribbon graph, so that all these edges are not really edges, but they're ribbons, and I'm connecting these ribbons in this clockwise procedure. So in this particular example, what I've created a graph which is drawn on the sphere, but in general, what I will get, it will be a graph which is drawn on an orientable surface, and it is drawn in a way that if I cut this surface along the edges, I will obtain a collection of topologically open disks. So they will be polygons. And I also promised you that the last permutation tells you something about the faces. So we can see on this picture that this permutation encodes the labels around faces of my map. So how do I do this? I should walk around the graph on my surface, starting from 1, and then I will read every second label. So here I have 1, then I don't read. I have 2. I don't read. I have 3. I don't read. 4. I don't read. 5. I don't read. And I'm back in the starting point. So this means that it has only one face, and this face is given by the cycle 1, 2, 3, 4, 5. So, okay, so in general, a map is a graph embedded into a surface such that it has this surface into simply connected pieces. And this procedure that I showed you is in fact a bijection between triple of permutations whose product is equal to identity and labeled maps which are not necessarily connected. But I told you that I would be interested in a logarithm of this tau function. So what does it mean in terms of maps? It means that I forgot my labels, but I keep only one label, let's say the first label. So if I do this is called a rooted map. And another way of thinking about it, which is more convenient for our purposes, is that a rooted map is just a map without any labels, such that it has a distinguished corner, which is also oriented. Okay, so here I denote this corner by this little arrow, and it is oriented like that because I was walking clockwise. Okay, so the summary of this whole discussion about this bipartite maps is that these tau functions that I've started from, that I was telling you that these are generating functions of branched coverings. In these special cases, when I have only 3 families of variables, this is nothing else, but this is just a generating function of the first one is a generating function of orientable, labeled, but possibly disconnected maps. And if I take the logarithm and TDDT, what I've got a generating function of orientable, rooted, and connected maps. And also the difference between these two is that in the first case I have an exponential generating function, so the coefficients are non-negative, but the second generating function is a true generating function. So this is really a generating function of orientable, rooted, and connected maps. Okay, but clearly this definition of maps, it makes sense on non-orientable surfaces because 2-dimensional real manifolds might be, of course, non-orientable. So there is this natural question: can we encode also non-orientable bipartite maps in the same way? I mean, using either representation theory or symmetric functions theory. And the answer is yes. So in terms of representation theory, now instead of looking at the representation theory of the symmetric group, we should look at the representation theory of the Gelfand pair, a symmetric group on 2n variables and its subgroup, which is a hyperoctahedral group. So this is a result due to Hanlon, Stambridge, and Stanley. And then Goulden and Jackson, a bit later, they noticed that you can write this generating function of non-orientable bipartite maps in terms of symmetric functions. And now instead of normalized Schur, we will use zonal polynomials. So here is the result. If you look at the generating function of non-oriented, rooted, and connected maps, so this is my generating function, and it has these 3 variables, such that each variable tracks important statistics in my maps. So the first one telling me what are the degrees of black vertices, the second telling me what are the degrees of white vertices, and the last one tells me what are the degrees of faces. Then this generating function is again a partition function of symmetric functions, which are called zonal polynomials. Okay, so this is a small summary. So we know that we have these orientable maps and non-orientable maps, and their generating functions are given by Schur symmetric functions and zonal polynomials. So if you are an expert in symmetric function theory, you can recognize that Schur symmetric functions and zonal polynomials, these are special cases of something which is called a Jack polynomial. And if you are not an expert in symmetric functions theory, I have this 2 lines crash course on Jack polynomials, which is telling you what are these things. So basically, you should think that Jack polynomials are certain symmetric functions which has additional parameter alpha, and they are constructed from the easiest symmetric functions, I mean monomial symmetric functions, using Gram-Schmidt orthogonalization process. So I think this is the easiest way to think about Jack polynomials. It doesn't tell you too many properties of them, but at least you can imagine how to create these Jack polynomials. So okay, let me rephrase this summary that I showed you. So we know that we can write these generating functions in terms of Jack polynomials, and I wrote them in a very specific way so that you can see that something is happening. And this is precisely what Goulden and Jackson noticed in '96 when they figure out how to encode non-oriented maps. And they pose this beautiful conjecture, which is still wide open. And this conjecture tells you that now if you take Jack polynomials with this generic parameter b, there is this funny shift here. So instead of taking alpha, now I'm taking 1 plus b. So if you take this generating tau function of Jack polynomials, the conjecture says that it's still the logarithm, the t dt logarithm of this function, it's still a generating function of bipartite non-oriented maps, but there is a mysterious statistic which measures non-orientability of your map. And it measures in the following way, that it gives you 0 if and only if your map is orientable. So you don't see this B here, only for orientable maps. And whenever your map is non-orientable, there is B to some mysterious power. Okay, so as I said, this is still wide open, and many special cases are proved, but the conjecture is open. And we were highly inspired by this conjecture, and together with Guillaume, we looked at, we used this point of view of Goulden and Jackson, and we defined this B-deformed tau function of Okunkov. So I showed you that there are two special cases of tau functions, and the first one was the fundamental function in the field. So we took this function, and similarly as Goulden and Jackson, we replaced Schur functions by Jack symmetric functions. And then we were wondering if a similar phenomenon happens, and we discovered that yes. So this is the main theorem. The main theorem is that the logarithm of our tau function, this is a generating function of rooted generalized branched coverings of the sphere. So this is something that we defined in our paper, and you can think that this is a generalization of branched coverings of the sphere that I showed you in the first slide, so that now your covering space might be non-orientable as well. And then you have all these parameters, infinite numbers of p's, infinite numbers of q's, which are telling you what is the geometry of your first two branching points. And then you have other variables which are telling you what is the number of points in the pre-image. But maybe you will prefer a more combinatorial version of this theorem. And the more combinatorial version is telling you that instead of looking at branched coverings, this is a generating function of rooted K constellations. So these K constellations, you can already expect it should be something that generalize bipartite maps, because when we had 3 families of variables, there were bipartite maps. So this is indeed the case. So this is a map which has additional labels on variables, and it has these local constraints that each vertex I has only neighbors I+1 and I-1, and they alternate around the vertex. And because I also have these extreme labels 0 and k, then the vertex 0 has only neighbors 1, and the vertex k has only neighbors k-1. So these are objects that we are counting, and it turned out that there is this mysterious measure of non-orientability such that the logarithm of our tau function is precisely a generating function of these K constellations with respect to this measure of non-orientability. So let me show you the last slide, which is an idea of the proof. So the proof has 3 parts. The first part is a part that should be clear for maps experts. So if you're a map expert and you want to understand the generating function of maps, there is one way you can do. You can remove the root edge from your map, and you can think what's going to happen with the geometry of your map. So this is a classical idea of Todd from 60s that he applied to planar maps, and then Lehman and Walsh, they applied it to higher genus maps. But we have this much more complicated objects, which are constellations. So you have to do it in a very smart way. You should not delete just a root edge, but you should delete something which we call the rooted branch. So there are some technical things to do, but okay, if you're an expert in your field, you have some ideas how to do it, and it still works. So the conclusion is that you can create the partial differential equation which uniquely determines your generating function. And now if you're an expert in symmetric functions, in Jack polynomials, then you can also try to do the same thing for the left-hand side of your generating function. So you look at the partition function of Jack polynomials, and then you use some properties like Peary rule and the fact that Jack polynomials are eigenfunctions of Laplace-Beltrami operator. And again, use your creativity, play with nested commutators, and if you know your field pretty well, you can create also another partial differential equation which uniquely determines your function. And there is a third part, which is a miracle. Namely, you have to prove that these two partial differential equations are in fact the same. And this was the hardest part of the proof. It took us basically 2 years. So 2 years ago, we knew that it's true, but it turned out to be annoyingly difficult and very technical. But somehow we managed to prove it. So that's how the proof works. So yeah, so I will finish. Thank you very much.
Thank you very much. I think we have a time for one short question.
I have a question, maybe not so short. But if you have two PDEs that are the same, how do you know that these PDEs are non-linear, right? So they have infinitely many solutions. How do you know that the solutions match?
So it is because of the initial conditions. So I told you that I have this tau function, and the PDE actually uniquely determines this tau function. So why is it true? It is because this tau function, I mean, you can look at it as a formal power series, and if you know what is the constant term of your function, then PDE uniquely determines the whole tau function. So this is how it works.
Okay.
I think
it was too quick for me. Can you focus the difference from the conjecture of Jackson-Golden and your? It's specified to the same when you put b equals 0 or not.
Sure. So yeah. So it's yeah. Due to lack of time, I was not able to discuss it too much. But so these two things are somehow different. So on one hand side, okay, I will show you again the definition of this function, of our function. So here we have this product of many jacks. We have k jacks. So if k is equal to 1, then this is a special case of the B conjecture. So the special case of our result is also a special case of the B conjecture, but also this special case actually covers basically everything that was known so far. However, if you take bigger k, this is not strictly comparable with the B conjecture. So you might think it's weaker and stronger at the same time. I mean, there is this intersection point when a special case of our theorem is also a special case of the B conjecture, which actually covers all the special cases that were proved so far. But then if you take arbitrary k, these two things are not strictly comparable.